Hello everyone, I Sai Nikita, MTech Key student from Mahindra University. As a part of Infrastructure Health Monitoring Codes project, we have done a project of damaged location of bridge using structure health monitoring under the guidance of Dr. Visalakshi. Let me give a brief introduction about this. We know that the civil engineering structures built according to the modern codes and designed for a service life of normally more than 100 years. But at the same time, there is a growing pressure to keep existing age structures in service, despite the fact that they have reached the original design lifetime. With bridges being a good example, continuous monitoring of critical aging bridges has become necessary due to the increasing of traffic loads, changing environments, extreme shocks, so that which can reduce their load bearing capacity and increase the risk of failure. So for that problem, the structural health monitoring is a best example in order to identify the structural problems before they become critical, endanger public safety and reduce the serviceability. One of the key objectives of this project is to identify the location of damage in a bridge model before it reaching to the critical state. The materials required are aluminium, bolts and nuts in order to fix the members and the PZT, piezoelectric sensor and LCR meter. Here we can see the materials. This is the aluminium which is used for the members and this is the gusset plate in order to connect these aluminium members, nuts and bolts and the PZT sensor and this is the LCR meter. In this, we have adopted the electromechanical impedance technique. The basic principle of this technique is that if the PZT is vibrated at a given frequency, it is also vibrated to the host structure which is attached to the PZT. And it is also again sensed by the PZT. In this process, if any change in the propagation of waves is observed, it will indicate the damage. And we have also adopted the statistical indices technique as RMSD, that is root mean square deviation, in order to identify the location of damage. This is the formula for root mean square deviation. In this, where X and Y, Xi and Yi are the real part of admittance of healthy and damaged state respectively. The methodology we adopted are, first we have to model the bridge, after that performing experiment on health bridge model and performing experiment on damaged model. After performing of the both state, we need to compare the conductance signatures in both the states, that is in healthy stage and the damaged stage. After that, identify the location of damage using root mean square deviation technique. Coming to the demonstration of this project, this is the model made with the aluminium as I discussed. Coming to the specification of this project, the length of the model is 1.2 meters, height of the model is 0.26 meters. The dimensions of the top chord are 0.9 meters and the bottom chord length are 0.6 meters. The connections we have used are bolted connections with 6 mm diameter bolts. After the completion of this model, we need to fix the PZTs at required positions. Here we have fixed the PZTs at 3 positions. One is near to the left support, one is at the center of the top chord and one is near to the right support. After fixing of these PZTs, we need to connect this coaxial wires to the this is crocodile cables which are connected to the LCR meter. The wires are soldered using the soldering machine. LCR meter is connected to the PC. Make sure that the computer should have the software called vPro. After connecting these cables, we need to give the frequency. Here we have given the frequency range of 100 to 300 kilohertz in order to actuate the structure. Here we can, after clicking on the run, we can see the conductance and susceptance signature. This is the conductance and this is the susceptance signature of the healthy state. Here we are taking the conductance signature and susceptance signature for the healthy state condition for the PZT1. Here we can see the signatures of the conductance and susceptance. After getting the signatures, we need to export this data to the Excel file. Here we can see the data of the conductance and susceptance signatures of the data files. See, here we can get the data like this. This is the frequency values, this is conductance, and this is the susceptance values for the PZT1. Same should be repeated for the PZT2 and the PZT3. After obtaining the conductance and susceptance signature for the healthy state, we need to create the damage at the required locations. Here we have created the damage at 3 locations. The first damage is created in between the PZT1 and the PZT2 at the gusset plate connection here. The damage is created in terms of loosening the bolt at 5 rotations. Here we are creating the damage by loosening the bolt at 5 rotations. 1 turn, 2nd, 3rd, 4th and 5th. After creating this damage, again we need to connect these cables to the connect these cables with coaxial wires which is connected to the LCR meter. Again we need to collect the data of the conductance and susceptance signatures. Here we can see the conductance and susceptance signatures of the damaged state for PZT1. Here we can see the data in the Excel format. Yeah, here we can see the damage values of conductance and susceptance signatures for the PZT1. The same should be repeated for the PZT2 and the PZT3. And now we are creating the damage at the PZT between 2nd PZT and 3rd PZT by loosening the bolt at 5 turns. 1, 2, 3, 4 and 5. Here we have created the damage. Now again we need to consider the we need to take the signature of the PZT1. See, here we can see the signatures for the damage condition 2 for the first PZT. The same procedure should be repeated for the 2nd PZT and 3rd PZT for the damage condition 2. And now we are creating the damage at this position also. Make sure that while creating the damage here, we need to tighten these bolts. Now we are loosening this bolt in order to create the damage 3. Again we need to consider we need to take the signatures of the PZTs for the damage 3 condition. Here we go. After obtaining the conductance and susceptance signatures for the PZT1, PZT2 and PZT3 for damage 1, damage 2 and damage 3 conditions, we need to export this data to the Excel file in order to plot the graphs for conductance and frequency graph and also to identify the location of the damage using RMSD technique. After exporting the data to the Excel sheet, we have plotted these graphs of conductance and frequencies of PZTs. Here we can see the first plot. The first plot is the conductance versus frequency of PZT1. This is the pristine state. The blue color one is the pristine stage of the PZT1. Damage 11 means the conductance signature of the PZT1 when we have created the damage at location 1. The same case with the PZT2. Here damage 1-2 means the conductance signature of the PZT2 when we created the damage at 1, and the pristine stage is blue color one. For clear understanding of for clear observation, we have taken up a specified range of frequencies where we can see the clear peaks. We have chosen the frequency range of 180 to 200 kilohertz. Here we can see the blue color one, the pristine stage one of the PZT signature, and the orange color one is the damaged one. And here we can see the condition for the PZT2 and the PZT3. This is the conductance and signatures of PZT in damaged and healthy state 2. Here the pristine stage of the PZT1 in the second case. Here the damage to 1 means the conductance signature of the PZT1 when we have created the damage at 2. Here same case with the 2, that is damage at 2 and the conductance signature of the PZT2. Damage to 3 means the conductance signature of PZT3 when we have created the damage at 2. These are the plots which we have explained for the clear observation. The conductance signatures for 180 to 200 and 180 to 200 at the specified range of frequencies for clear observation. Here we can see the variations of the graphs of the conductance signature, the PZT3. This is the conductance and signatures of PZT in damage condition 3. Here we can see the conductance signature for the PZT1 in healthy state, which is indicated in the blue color, and the damage condition for the PZT1 is indicated in orange color. For the clear observation, again we have taken the frequency range of 180 kHz to 200 kHz. Here we can see the variations of these graphs. Here we have chosen root mean square deviation technique in order to identify the location of the damage. If we plot the RMSD versus patch number, we can see that for the damage 1 condition, the variation of the RMSD is more near to the PZT patch 1. That means the damage is more near to the PZT1 patch. Coming to the damage 2 condition, the RMSD variations are more near to the PZT3. That means the damage is near to the patch 3. Whereas in damage 3 condition, that is where we have created the damage in between 1 and 2 and 2 and 3. Here we can see the more variation of the RMSD at 3, that is PZT patch 3. So that it indicates that the damage is near to the PZT patch 3. So in this way we can identify the damage using RMSD values. The main outcomes of this project are the location of the damage is identified based upon the RMSD values, and also the critical location of the model is identified using this RMSD technique. Coming to the conclusion, if there is any damage in the structure, there will be change in the admittance signature. So these admittance signatures are used in order to identify the location of the damage. So in this way, the structure health monitoring is very effectively used in order to identify the damage before reaching the structure to a critical stage. So by this way, we can reduce the maintenance cost, and also we can enhance the service life of the structure, and we can also save the loss of life and the property. These are the references. Thank you one and all.